All right, guys, welcome to lesson 5 of unit 3. Today we're going to be doing limits when we're looking at mainly a direct substitution. Okay, that's one of our big ideas there is how to find a limit using something called direct substitution. So so far we've been finding limits by using tables. That's like an approximation method. And we've been finding limits using graphs. But today we're going to begin the process of finding limits by looking at equations only. Okay, and the first and most basic way to find the limit of a function whenever you're just looking at an equation is this method here called direct. So that's where we're going to start. After that, we're going to use that skill of direct substitution to start finding some limits of piecewise functions as they're written as equations. And then we're going to build on what we learned about continuity and decide if piecewise functions are continuous or not. Okay, so three topics for this lesson: direct substitution, applying it to piecewise functions, and then finally seeing if they are continuous or not on that basis. Okay, so let's go ahead and begin. So if a function is not continuous, then that means that the limit of the function as x approaches c is not the same as f of c because of such things as holes. Like in this graph here, you have a little blank spot for some reason. So in this case, the limit would exist. The limit would be 1, but the function doesn't exist at that point. Or you have jump discontinuities. So even though the function exists, the limit doesn't exist, and therefore you can't have continuous function. But if a function is continuous, then not only does the limit exist, so let's say we're talking about this point here that I'm highlighting with a square, not only does the limit exist, because as we approach from the left and as we approach from the right, they're both going to the same spot, but they also both land at a spot that is defined by the function as well, and that function equals the limit. So that's what makes something continuous, and as we mentioned, a continuous line is one where you can draw a line through without picking up your pencil. So, but what I really want to draw your guys' attention to is this equation. This is kind of significant, because here's the deal. I'm going to be asking you guys today to find the limit of a function given its equation. Well, all the functions I'm giving you today are going to be continuous functions. So if you want to find the limit of these functions, all you have to do is plug this number here into the function, and that will tell you what the limit equals, because the value of the limit does equal the value of the function at that point. So that's the direct substitution method. Just basically take the x value you're trying to approach and plug it into your function to get the output. Okay. So what is direct substitution? If a function is continuous at x equals c, that means the limit exists, the function exists, and they both equal each other. Then we can find the limit of f of x by simply finding f of c, because they're equal in the case of a function being continuous. Okay? So when can you use direct substitution and when can you not? Well, sadly, it's pretty rare that you'll be asked questions where you use direct substitution, and the reason for that is because, well, what's the point? You're basically just plugging in a number, getting an answer, and that's stuff that you learned back in Algebra 1, so those aren't real popular limit type questions. But it is a reality. You can do it. And so when can you do it? When can you not? Well, you can do it anytime a function is continuous. As we saw last class, polynomials are continuous everywhere, as are exponential functions. Now, you can also do it to rational functions so long as the number that you're doing it with doesn't make the denominator equal 0. It cannot happen where the discontinuity is. But so long as you're finding a limit where there's no discontinuity, then you can do direct substitution. You could do direct substitution with square roots also, so long as you don't get an imaginary answer. Or trig functions, so long as it's not on the asymptote. Or log functions, so long as it's not making the argument less than 0. So long as you can do direct substitution anytime you're not at a discontinuity. If you're at a continuous part of your function, then you can do direct substitution. So let's go ahead and do this here. I'm calling this guided practice, mainly because I'm going to show this to you guys, and then you're going to kind of get it, like, oh, okay, well, that's like extremely simple, and so we're just going to move on after that. The last one will probably make you think a little bit, just I know you guys probably don't prefer trig functions. Number 2 will probably be pretty good. All right, so first of all, notice that that's a just a polynomial function there. That's a linear function, which is a polynomial, and they're continuous everywhere. So since this is a continuous function, I can use the method of direct substitution to figure out what is the limit of this function. Okay, and according to the method of direct substitution, all we have to do to find this limit is we just have to plug this value for x into our function. So 2 times negative 2 is negative 4, and that's it. All right, so I would encourage you guys to pause the video and try to do it on these two. Now, just so you know, I think I'm pretty sure both of these are just going to be. I know that the number 2 is continuous because it's a polynomial, so you should be able to do direct substitution problem. Cosecant, yeah, you're good. This is not going to be discontinuous, so you can do direct substitution. So it's just a matter of you remembering your trig circle. And remember that extra credit's still up anytime you want to do it. Anyway, so go ahead and pause the video here and do direct substitution on these two limits to evaluate their values. When you pause it, you'll see the solution. All right, so the answer number 2 here, if you plug in 2, is, I got 32. Let's double check that. 8 plus 20 is 28. Plus 6 is 34. Minus 2 is 32. Now for number 3, you're just plugging in your 3 pi over 4. So cosecant of 3 pi over 4, that's going to be the same thing as the reciprocal of sine of 3 pi over 4. Come to think of it, I think I just did a whole bunch of convoluted mess here. But anyway, you get the reciprocal of sine, right? Which is, and the sine of 3 pi over 4 is radical 2 over 2. And if you take the reciprocal of that expression, then you get 2 over radical 2. If you rationalize it by multiplying the top and bottom by the square root of 2, and I multiplied, well, actually, first of all, I multiplied 4. And then I rationalized. I multiplied the top and bottom by the square root. I got this, and then I reduced. So the final answer is 2 square root of 2 for that one. That's just Mr. Bailey being me. All right, but got to do those trig functions. Don't give up on them. Okay, let's go ahead and take a look at another example. So now that we know what direct substitution is and how to do it, basically you're just going to plug it in. We're going to practice doing direct substitution on this piecewise function. Now piecewise functions are interesting. Okay, what a piecewise function is, in case you forgot, is it's a function that's basically broken up into 2 pieces. Okay, so basically we have the function negative x minus 3 for all values of x that are less than negative 2. So I'm going to draw a line here, and I'm going to go to where x equals negative 2. So the function is negative x, negative 3 for all x less than that. So it's gonna look something like this. Okay, but once we get to x equals negative 2, like right about here, the function's going to stop. And then for this piece, x minus, now you guys don't have to draw this, okay? I'm just kind of explaining to you what a piecewise function is. Probably been a while since we've seen one. But for this one here, we have x minus 1 is the function for all values of x that are greater than 2. So from here, we have the function x minus 1. So that's probably going to be something like that. And that's what a piecewise function is. Now it's not, I actually didn't draw it very good, but it's going to look something like this, okay? And that's a piecewise function. So basically for all x less than or equal to negative 2, it's this function, which is the one on the left. And then for all values of x greater than 2, it's this function, which is the one on the right. Okay, and that's what a piecewise function is. Now we want to find what is the limit of this function as x approaches 2. All right. Well, let's go ahead and do this. So when you're doing piecewise functions, you have to draw, you have to do the limit from the left and the right. This would actually be a pretty good little note to write here, okay, on your notes. When finding the limits of a piecewise function at its boundary points, what do I mean at the boundary point? Well, if I asked you guys to find the limit right here, you could just do direct substitution. You're going to get a good answer because there's no holds, gaps, or jumps. But at a boundary point, when you're looking at an equation, I don't know. Is this piece connected to this piece? Well, the way I drew it, it isn't. But what if I drew it wrong? Maybe this piece actually belongs down here, so it looks like this, and they actually do connect at a common point. I'm not sure. Okay, unless I'm actually very careful in how I draw this and draw it correctly, I might be wrong. So either this piece is up here, or it's down here. If it's up here, it doesn't connect to the other piece. If it's down here, it does. If it's up here, the limit wouldn't exist because I would have a jump discontinuity at that point of -2. But if it's down here, they do connect, and therefore it would be continuous at that point. So if you're trying to find the limit at the boundary point, or at the end point, I'll call it, the end point of the pieces, if you're trying to find the limit of a piecewise function at its boundary or endpoint, then what you'll need to do is you'll need to find the limit from the left and the limit from the right. And our goal is to see, do they meet up at the same point? If they do, then the two pieces are connected. But if I find the limit from the left and I get a different answer than if I find a limit from the right, then that means they're not connecting, and this function therefore would not have a limit at that point. Okay, so this is a very important little note to write on your notes for today, and then I would encourage you to underline this and just draw a line to the -2, because that's what it is. The boundary point is -2. That's where the pieces connect together. Okay, but anyway, that's enough explanation, and I think I do have a little bit of a typo here I need to fix. This is supposed to say negative right there. All right, so I want to know, what is the limit of f of x as x approaches -2? Now notice that's the boundary point, okay? And as I said, when you're trying to find the limit of a piecewise function at its boundary point, then you need to find the limit from the left and the right. So let's do that first. First of all, I want to find, what is the limit of this function as x approaches -2 from the left? And then I want to find, what is the limit of this function as x approaches -2 from the right? Okay, well, if I'm approaching -2 from the left, that means I'm approaching -2 from numbers that are smaller than -2. So let me ask you guys, which of these inequalities represents values of x that are smaller than -2? I'm going to say the whole question again. If I'm approaching -2 from the left, then that means I'm approaching -2 from numbers that are smaller than -2. Which of these inequalities indicates that I'm approaching, which one of these inequalities are x values that are smaller than -2, or maybe I could say less than -2? It's this one. All right. So since that is the one that is less than, it goes with the left. So here's what I want you guys. Here's another good little note that we can write here on our notes for this section. Let me bring up a try to find a better way to type. So whatever number you have a little negative here, that's going to go with the inequality that says less than. So therefore, if I'm approaching -2 from the left, I'm going to use the piece that is associated with the less than there. So let's go ahead and write that. So the limit then, as x approaches -2 from the left, of which piece? This piece. Because that's the piece that goes for x less than. And all we have to do now is do direct substitution. So I'm going to plug my -2 in. It's going to give me the following. Notice the negative outside the parentheses and inside cancels, so you end up with a positive 2. And positive 2 minus 3 is negative 1. So let's review that really quick. When finding the limit of a piecewise function at its boundary point, we have to find the left-handed limit and the right-handed limit. Now for the left-handed limit, we're going to use the piece for where x is less than or equal to negative 2. So we're going to do direct substitution with this part of the equation. So I'm going to plug the negative 2 into the top half. Now in the bottom half, we're approaching negative 2 from the right. Well, what do you think I'm going to add as a note for this? There it is. If you're approaching a number from the right, that means you're coming at negative 2 from numbers that are bigger than 2. And this is the inequality that represents x values that are bigger than 2. In other words, x is greater than negative 2. So for this one, we're going to use this piece. So the limit of f of x as we approach negative 2 from the right is going, as according to this inequality here, telling us we're going to plug it into this function. So we're going to do the limit as x approaches negative 2 from the right, minus 1 there. Once again, we're going to do a direct substitution. So if you plug that in, you're going to get negative 2 minus 1, negative 3. Okay, so what I want you guys to notice here is that the limit from the left is negative 1, and the limit from the right is negative 3. Do these two limits on the left and right match? No, they're different. When I'm approaching negative 2 from the left, I get negative 1, which would probably be like somewhere up here on the y-axis. Actually, below. So if I'm approaching the negative 3 mark, right, it's going to end up at negative 1. That's if I'm coming at it from the left. But when I'm approaching f of x, if I'm approaching negative 2 for the function f of x on the right, I get a limit of negative 3. So this one actually ends up being way down here. And so my original picture was actually more correct. So does the limit exist at negative 3? Negative 2? Oh, I was doing negative 3, but it's negative 2. Doesn't matter though. No, it doesn't, because the limit from the left and right are the same. So I'll review one more time. When finding the limits of a piecewise function at their boundary point, then you need to find the limit from the left and from the right. When you're finding the limit from the left, you're going to use the piece that is associated with the x is less than. So in this case, negative x minus 3. And when you're approaching the boundary point from the right, you're going to use the piece associated where x is greater than. And then you just do direct substitution. If they don't match, that means that the limit does not exist. If they do match, then that's the limit. So let's say I just got both of these to be the same number, like let's say they're negative 1. Well, then my answer would be negative 1, and that would mean that those two pieces actually connect at negative 1. Okay, but in this case, that's not what happened this time. So here's one for you guys. Let's go ahead and have you guys give this a shot. Let's try this one here on the right first of all. All right. Go ahead and see if you guys can show your work appropriately. Once again, we have a piecewise function. We're approaching the boundary point or the endpoint, negative 3. So you're going to need to do a left-handed limit and a right-handed limit. And go ahead and see if you can show your work and arrive at the correct answer. I'll pause the video here, and when you unpause it, you'll see the solution. So the final answer to this one is 1. The limit did exist. So we need to find the limit from the left and the limit from the right. For the limit on the left, we're going to use the piece that is associated with the x is less than or equal to negative 3. So we're going to be plugging negative 3 into x squared plus 4x plus 4, which would give me 1. And then when we're approaching negative 3 from the right, then we're going to use the piece that's associated with the x is greater than negative 3. So we'll be using the 2x plus 7 for that side. And then we just do direct substitution, and when you plug that in, you get 1. So the limit from the left and the limit from the right are the same. They meet up at the same point. Therefore, this piece connects to this piece, and therefore, it seems to be continuous. We can't really be too sure it's continuous yet, but that's a good start. The pieces at least meet up. and the limit exists. Therefore, we can say that the limit is 1. Now, let's go ahead and take a look at this next one over here. I want you guys to see if you can figure out how to do this one. This is a 3-piece function, okay? We have this piece for all x that are less than or equal to -3. We have this piece for all x between -3 and 5. And then we have this piece for all x greater than 5. So I want you guys to find the limit of this function as x approaches 5. Now 5 is one of the endpoints. There's 2 endpoints for this one because there's 3 pieces. So go ahead and see if you guys can accurately calculate this. Now pause the video. When you're done, you'll see the solution. Okay, so taking a look here at this one, since 5 is a boundary point, then we need to find the limit from the left and the right of that boundary point. So if I'm going to approach 5 from the left, that's what the little pink negative there is, that's going to be associated where x is less than 5. And so I'll be using the piece 2x plus 7 to evaluate that limit. So we plug in -5, which gives us -3. Now for the next one, we're approaching 5 from the right with our function. Now when you're approaching 5 from the right, that means that you are approaching 5 from values that are greater than 5, so that means we're going to use the piece associated with x is greater than 5, and that piece is x over 10. So we'll be doing direct substitution, plugging 5 in here in the top. 5 over 10 gives me a half. Now as you can see, the limit from the left and right are different, so that means that this piece, the pink piece, is not going to connect with the blue piece. It's a jump discontinuity, and therefore the limit does not exist at that point. The limit from the left and right are not the same. So there is your student practice for that. So now we're going to take it one step further, and we're going to answer a more a fuller question now. Instead of just finding the limit, now I'm going to answer the question, is the piecewise function continuous at the indicated value of c? Now I just want to warn you guys here, this is a good little thing to write down in your notes, that this is a really common FRQ question, and you'll definitely be seeing it on an FRQ question in this class. The types of questions you'll see with these is you're going to get a piecewise function, and basically what we have to do is we have to determine, is this function continuous at the indicated value of c? Is it continuous? Now remember, what does it require for a function to be continuous? Well, the limit has to exist at that point. So here's the c value I'm trying to see if it's continuous. So the limit at that point has to exist. In other words, the limit of f of x as x approaches 0 has to exist. Also, f of 0 has to exist. Finally, those two things have to be the same. Okay? So that's how you can determine if a function is continuous at that point or not. So the first thing we're going to do is exactly what we did on the last slide. We're going to determine, does the limit exist first? And so to do that, since this is a boundary point, and it usually will be with these types of questions, we're going to have to find the limit from the left and the limit from the right. If they match, then hooray, the limit exists. And then if we find out that the limit exists, we have one more step to go. We're going to find, well, does the function actually exist at that point? If it does, hooray. And if they match, hooray even more. That means hooray, it's continuous. I don't know why I keep saying hooray. That's weird. I'm getting tired. Okay. Anyway, let's go ahead and do the problem here. So I'm going to make some space for me. I would encourage you guys to show your work exactly the way that I do. It's just kind of nice. It's the way I put together after a couple of years. It's pretty clear to the point. So what we want to do is first of all, we want to find the limit of my function as x approaches the c value that they give us. Okay. Now to do that, we need to find two separate limits. I need to find the limit as x approaches 0 from the left, which is going to be this piece. And I also need to find the limit as x approaches 0 from the right, which is going to be this piece, because that's where x is greater than, right? So let's go ahead and do that. So the limit for this one by direct substitution is going to be -2. How about this one here? If I plug that in, oh, what do you know? That's also -2. Those are equal. What does that mean? That means that the limit exists and it equals 2. But now the question is what does f of 0 equal? What does f of 0 equal? Okay, well, to do that, all you have to do is come back over here, and you just have to find the piece where it says x equals 0. So notice this says x is less than 0. That's no good. But look right here. This says x is greater than 0, but you know what it also says? It also says x can equal 0. So you're going to look for the piece where x can actually equal 0, and that's the piece you're going to use whenever you're just trying to find out what the function actually equals. Okay, so let's do that. So f of 0 is, we're going to use the -2x minus 2 for that. We're going to plug in 0, and voila, we get -2 again. Well, the limit from the left is -2. The limit from the right is -2. Therefore, the limit is -2. And then, I forgot to put my negative. And then the function's value, just plug 0 into the bottom piece, and you get -2 again. All three of those are equal. So as you guys can see, the limit is equal to the function at that point. And therefore, we would say, yes, this is continuous. And our reason would be everything that we wrote. Okay, so this is our reason. So on an FRQ, they would want to see all this stuff. The answer is continuous. Now, they'll give you the point, but they'll only give you the point if you actually give the reason. So you have to show that, yes, you found the limit from the left and right to prove that the limit exists and what the limit is. And this, whether or not you have to do f of 0 is kind of silly, because honestly, this and this are identical anyway. But just to be safe, we're going to show the process of plugging in the point to the part with the equal sign, just to make sure we're covering all of our bases and proving every part that needs to be proven. There it is. So this function would be continuous, which means that these two pieces would actually connect to each other and there'd be no holes, gaps, or jumps. And that's why I had the graph here in the beginning, because as you guys can see, this here is the first piece, and then you see the bend all of a sudden that happens there. That's the second piece. And they connect right there at x equals 0 and y equals -2. So as you can see, there's no holes, gaps, or jumps there. So that's a continuous function because the limit existed at that point because it was the same from the left and right. And the y value existed at that point and it was the same as the limit. So that's a continuous function. All right. So let's have you guys try one of these. So we're going to do the same thing, but this is a guided practice. So this means I'm going to let you guys walk through it with me step by step. Okay, so here's my piecewise function, and I want to know, is it continuous at -1, which is the boundary point? Okay, all right. Well, the first thing that we need to do is, like I did on my last slide, is the first thing you need to do is you need to find the limit as x approaches that boundary of your function. And the only way to do that is by splitting it up into two separate limits and doing it. So I would like you guys to pause the video here, find the limit from the left and right, and see if they're the same. If they're the same, go ahead and state what the limit equals. Okay? When you unpause it, you'll see the solution. Now, I'm not showing a whole lot of work here, especially the plugging in part. I'm just kind of doing that part mentally. But basically, the limit is 3, because the limit from the left and the limit from the right is 3. Therefore, the answer is 3. So the limit from the left, you're going to use the piece -x plus 2. Plugging -1 into this, the negatives cancel, so you're left with 1 plus 2, which is 3. For the next one, plugging in -1, you're left with -1/2 plus 7/2. If you put those together, you're left with 6/2, which is 3. The limit on the left and right are the same, and therefore the limit exists. All right, now what's the next step? After we find the limit, what else do we have to prove exists? We have to prove that f of -1 exists. We actually have to find where can I plug this in. So I want you guys to go ahead and pause the video here and give that a try. When you're all done, go ahead and unpause it, and then you'll see the solution. Well, hopefully you guys got it doesn't exist. Because I told you guys that if you ever want to plug this number in, you have to find the piece where x is equal to that number, and there isn't one. So therefore, you're not actually allowed to plug -1 into either piece and call that the answer. So even though the limit existed, the function didn't exist, and we're going to say not continuous since, and then we'll just draw an arrow to that, f of -1 does not exist. So it's not continuous because the function doesn't exist. And that's our answer to that one. All right. Once again, I'm going to show you guys a graph. Now, you don't usually get a graph, but I want to just tie this into the graph because we're familiar with graphs at this time. So let's take a look at the graph. So as you guys can see, the limit from the left and the limit from the right do meet up at the same point here. They meet up at that open dot. So the limit exists, and the limit is 3. The y value at that point is 3. However, the dot's not filled in, and there's no dot anywhere else. So the function doesn't actually have a point there. So even though we're approaching the same point from the left and right, and therefore the limit exists, the function doesn't. And so since we have a hole, we have a gap, and if you try to trace that line, you'd have to pick up your pencil before tracing the rest of it, because the function is not continuous, and that's because the function doesn't exist at that point. All right, let's do one more guided practice. So for this one, this is and when I said one more, I mean one more guided practice. I'm going to give you guys a student practice where I just let you guys do the whole thing from beginning. All right, but like I said, we're kind of going through these steps. All right, so is this function continuous at the boundary point 0? That's our c value. So what's our first step? What do I have to find first? Hopefully you thought, well, Mr. Bailey, I need to find the limit first. And if you want to find the limit of a piecewise function at its boundary point, what do you have to do? Hopefully you were thinking to yourself, well, Mr. Bailey, I have to find the limit from the left and right separately. So pause the video here and see if you guys can set this up appropriately. And when you unpause it, you'll see the solution. Well, here's the limit from the left, and here's the limit from the right. And this one comes out to be 0, and this one comes out to be 2, which means the limit does not exist. Well, I don't need to bother with the next step. Typically, on the next step, what we would do is we would find, okay, well, what's the value of f of 0? But we don't really even need to bother with that. Why not? Because the limit doesn't exist. And if the limit doesn't exist, then the function can't be continuous. So we're going to say the function is not continuous at x equals 0 since, and there's my answer, the limit does not exist at that point. So on your FRQ, when you guys are doing these things, you have to say whether it's continuous or not, and then your explanation is all the work that you showed. And so you want to make sure you're showing your work in the way that I'm showing you here. Now, let's go ahead and take a look at the graph and see why that is. Here's the graph. And as you can see, we have a jump discontinuity. The limit from the left is 0, but the limit from the right is 2. So we have a jump discontinuity. Now, the function is defined at 0. It's right there. We've got a closed dot at 0, but it doesn't matter if the function is defined or not. We have a discontinuity because the limit doesn't exist. So there's our picture that matches our answer. All right, now for the last one, I'm going to let you guys do the problem completely on your own. So your job is going to be to do all of it from beginning to end. So see if you guys can find the answer. Now, but before you begin, I just want to point something out. This is kind of a weird piecewise function. And so I want to write it a little bit differently for you guys. And I'm going to highly encourage you guys to write it this way as well on your notes, because it'll help you in the future when you see these. So what this piecewise function here is saying is it's saying that f of x is equal to 5 when x equals 2. But anytime x is not equal to 2, we use this piece to find the answer. Okay, so instead of saying x is not equal to 2, let me show you what else we can do instead. And I think this is a much better way to write these. However, the reason why people write it this way is because it's shorter. And so you will see it, and so you want to get used to it. But as you guys know, as if x equals 2, then the function equals 5. But for all other values of x, we use this, right? Which means that if x is less than 2, we use this. And if x is greater than 2, we use this. All right. So now that we've rewritten it, now I'm going to ask you guys to go ahead and see if you guys can find the answer. Is this function continuous at the boundary point 2? All right, go for it. Well, here's all the work. If we want to find the limit from the left and the limit from the right, finding it from the left, we're looking for the places where x is less than 2. And so that's going to be x squared minus 4. And then finding the limit from, as we approach 2 from the right, that's going to be for x values greater than 2. So we'll use this piece. So they both have the same piece. So obviously when you plug 2 into both, you're going to get the same answer. So the limit exists. The limit is 0. Now what's f of 2 though? So that's the part where we look for where x equals 2. And that's here. What's the answer? 5. So f of 2 is 5. So even though the limit exists, and even though the function exists, we still have a problem. They're not the same. Not only does the limit have to exist, but it has to equal the function. And so the final answer to this one is not continuous at, I'm sorry, I'm writing over the writing, it's kind of ghetto, but at x equals, I know what I can do. A little less ghetto looking. That. Boom. All right. Not continuous at x equals 2 since, and then here's your answer, because the limit is not equal to the value of the function at that point. Now I want to show you guys the graph that goes with it. Okay. Here it is. So the limit from the left is 0, and the limit from the right is 0, but the value of the function is 5. We have a hole with a dot above it. In that case, even though the function exists and the limit exists, since that dot is not in the right spot, it's still a gap, and therefore it's not continuous. So I strategically picked all of these examples to give you guys a bunch of different scenarios that are pretty common you want to be aware of. So, you know, our first one I gave you here was, yes, it was continuous. The limit was the same on the left and right, and the y value was the same, so therefore it was continuous. Then I picked one where the limit existed, but the function didn't, because there was no equal sign anywhere. Another one I gave you was where the limit just failed to exist because it was a jump discontinuity. The limit from the left and the right weren't the same, so it wasn't continuous. And then finally I gave you this funny thing. So when you see this not equal to, just rewrite it with this one in the middle, and then write this one twice, one where it's less than, one where it's greater than. That way when you're doing your limits from left to right, you'll know which piece to use. But regardless, this one turned out to be not continuous because even though the limit existed and the function existed, they weren't the same. Okay, so those are all the possible scenarios you could possibly encounter when doing these kinds of problems. But there you guys have it, and that's going to end our lesson for the day. So, hope you guys enjoyed it. We'll see you next time.